Greetings. Today we're going to cover section 7.4, and this is probably, in my opinion, the most interesting section in the entire book. It's very theoretical, but I don't think it's hard to understand. And basically what we're going to be talking about today is infinity. And the remarkable result that we're going to see in this chapter is there are many kinds of infinity. This is quite a remarkable result. So it would probably be best to just start off with the easiest kind of infinity, the first kind of infinity. First of all, let us review. We have this set here called the natural numbers, which look like this: 1, 2, 3, 4. And yes, it does go to infinity. And we ask the question, how big is this set? Well, before we answer that question, I want to talk about something else. I want to talk about functions. Remember, we're in a chapter on functions. From the natural numbers to some arbitrary set, we'll just call it A, where f is 1 to 1 and on to. Well, let's consider an example. Here's a real simple one. We'll just say that f of n is equal to n. So that's a function that sends the number 1 to 1, and it sends the number 2 to 2, sends the number 3 to 3. And I think if you give this a little bit of thought, you would agree that f here, f is 1 to 1 and on to. Let's consider another one. So suppose I were to tell you I want to take f of n and I want that to equal 2 times n. Well, so 1 would go to 2, and 2 would go to 4, and 3 would go to 6. And again, if I define my set A over here, if I were to tell you that A is equal to this set, up to infinity, I think you would agree that this function here, f, that maps the natural numbers to A, that this is also 1 to 1 and on to. And I think given that example, it's very easy to construct other ones. For example, we could talk about f of n is equal to 7 times n. And again, if I have my set n over here, and that's equal to 1, 2, 3, forever and ever, and over here I would have my set A, which is equal to 7, 14, 21. And again, we would see that 1 would map to 7, and we would see that 2 would map to 14, 3 would map to 21. Okay? Again, we could see that this is 1 to 1 and onto. So I want to come up with a definition here. Actually, there are a lot of different terms that all say the same thing. And I want to say suppose f is a function that maps the natural numbers to some set A, and that f is 1 to 1. It's 1 to 1 and it's onto. Then we say the set A is, and here's where there's several terms that all mean the same thing. One thing we would call it is we would say it's infinitely countable. Another word for this is we would say it's denumerable. Another word, it almost sounds like the same thing, we would say it's enumerable. These three terms here, infinitely countable, denumerable, enumerable, they all mean the same thing. Okay? It means that there is a function f from the natural numbers to a set that is 1 to 1 and onto. Okay, so the first question we have how big is n? Well, first of all, we certainly see, we know that we can have a function f that, and we already did this, that maps n to n. Just that f of n is equal to n. So that means that the set n is denumerable. Now you may recall previously when we had sets, we talked about the order of a set. For example, if I had a set 1, 2, 3, we came over here and we talked about the order of the set, or the size of the set. And we would say that this thing over here is 3, the order of a set. So the question we have here is what do we want to say about the order of the natural numbers? And what we're going to do is we're going to create a symbol here to say how big that set is. Now that set is certainly infinite, but it's denumerable, okay? Denumerable means we can make a list of it. In other words, if I were to say to you, what is the 23rd element in this set? Well, if I use this function over here, the answer would be 23. If I were to say to you, okay, you have a list of natural numbers, what is the 109th natural number? Well, according to this function over here, it's 109. So we use a funny symbol to indicate how big this set is, and I'm not very good at drawing this. And that is called Aleph null. The man who came up with this idea about 150 years ago, a guy named Cantor, he decided to use a Hebrew letter, Aleph, and he called this Aleph null. So we would say that the order of this set is Aleph null. Now that is infinity. We're going to show that there are other infinities other than this in a few minutes. But again, if you consider some of the other sets that we've talked about here, I'm going to call this set over here, I'm going to call it 2n. And we've seen this one before, this one right here. And we said we can define a function from n to 2n where f of n is equal to 2 times n. And we also remarked that this function right over here is one-to-one and onto this set. So that means that 2n is also denumerable, which means that the number of elements in this set is equal to this funny looking number right over here. Okay? Now this is a very interesting thing to note here. Note that what we have here is we have that 2n is a proper subset of n. Yet they both have the same number of elements. Okay, that's a property of infinite sets. It is certainly not the case for finite sets. For example, if I come over here and I have A is equal to 1, 2, 3, and I have B is equal to 1, 2, 3, 4, it is clearly the case that A is a proper subset of B, and the order of A is less than the order of B. So in fact, we can even say the following. If A is a subset of B, and the order of A equals the order of B, then A and B are infinite. Okay, that's a very interesting result right there. Now, I promised you there were other kinds of infinity, and we're going to look at some other infinite sets, and we're going to decide whether they are the same kind of infinity or not. So what I want to do here is I want to consider Q. Now these are the rational numbers. And remember, the rational numbers are equal to the set of all A over B, such that A and B are contained in Z, and B doesn't equal 0. Now remember what Z was. Z, I'll just put it over here in case you forgot, Z includes the negative integers. -3, -2, -1, 0, 1, and it goes on like that. Okay? I guess the other set that we're going to want to look at, why don't we also look at Z? Okay? And I guess the other set that we're going to look at, okay, so these are the integers. And these are the real numbers. So I guess maybe we should do this one first, and then we'll do this one, and then we'll take a look at this one over here. So, let's consider Z. Now remember, if we want to show that Z is denumerable, what I have to do is I have to give you an explicit list. In other words, I have to be able to say to you, here's the first integer, here's the second integer, here's the third, here's the fourth, here's the fifth, and this goes on and on. And the way to think about this is this really is a function from the natural numbers to z. Well, I can do this in a lot of ways, and watch how I'm going to do this. I'm going to come over here and say that 1 goes to 0. And then what happens is I'm going to go over here. So I'm going to say that 2 goes to 1. And then from there, I'm going to come over here, and I'm going to go to 3 goes to -1. And then what happens is I'm going to come over here, and I'm going to say that 4 goes to 2. And then I'll come over here, and I'll say 5 goes to -2. And I think you can start to see the pattern, okay? 6 is going to go where? 6 looks like it will go to 3. It looks like the 7 will go to -3. And I think you're convinced, you can see that what I'm doing here is I keep going back and forth like this, okay? And ultimately what I'm going to do is I'm actually having a mapping, okay, a function from the natural numbers to the integers. Now, it would be nice if I could come up and just say f of n is equal to something, okay? And maybe we can look at this and we can figure out some way to do it, but it's not really necessary. I think you are willing to believe that this list goes on forever and ever. On the left side, I've got the natural numbers going in ascending order. And I think that you're willing to believe that on the right side, okay, I am ultimately going to list every element in this set right over here, okay? I think we can almost figure out what the function is. It looks like the even numbers go to exactly 1/2 of them. So I'm going to come over here and I'm going to say, if n is even, then f of n is equal to n over 2, okay? If n is odd, then what can you say about it? Well, it looks like it goes to n minus 1 over 2, but with a minus sign in front of it. F of n is equal to n minus 1 over 2 with a minus sign in it. Okay, and we can see that that even works for 1. If I come over here and I have a 1 in front of it, 1 minus 1 is 0. 0 divided by 2 is 0, and I stick a minus sign in front of 0. Minus 0 is just equal to 0. So here's the explicit function right over here. But again, I want to emphasize that it's not necessary to come up with the explicit function if you can come up with an explicit list. Okay, so what's our conclusion here? Z is denumerable. Or in other words, the size of this set is again equal to this thing called Aleph null. Okay? Moving along. Okay, so you may recall before we talked about Q. But what I want to do is I want to talk about Q plus, the positive rational numbers. So what that's equal to is the set of all A over B such that A and B are contained in the natural numbers. And I don't even need to say and B doesn't equal 0 because the natural numbers don't contain 0. So I'm just going to say this. Okay? Now, what I want you to do here, watch this very closely because we're going to be doing stuff like this again and again and again. What I'm going to do is I'm going to I'm going to make a square here, and I want you to watch how I do this. This is going to be 1 over 1, 2 over 1, 3 over 1, 4 over 1, and this goes on forever and ever and ever. And then I want to come down a row, and I want to do 1 over 2, 2 over 2, 3 over 2, 4 over 2, and that goes on forever and ever. And I'm going to come down here, and I'm going to say 1 over 3, 2 over 3, 3 over 3, 4 over 3, and that goes forever. Likewise, this goes down this way forever. Now, what I want to do is I'm going to create a function f that maps the natural numbers to q plus, and this is going to be 1 to 1 and on to. And here's the way I do it. I come over here, and this is f of 1. And from here, I come over here, and I look at this, and I ask the following question. Is this already in my list? And the answer is no. Right now, 1 is in my list, and I'm adding 2. So I'm going to call this f of 2. And then from here, I'm going to come down to here, and I look at that. And I ask, is this in my list? Well, so far I've got a 1, and then a 2, and here's a half. It's not there, so I'm going to add it to the list. So I'm going to call this f of 3. And now what I'm going to do is I'm going to go down this way. And I've got 1/3, and I ask, is that in the list? And the answer is no. So I'm going to call this f of 4. And now I'm going to come back over here. Well, 2 over 2 is 1, and that is in the list. So I'm not going to add it to the list. All right, well, from there I'm going to come over to here. And I look at this one, and this is 3. And 3 is certainly not in the list. So the last thing I had was f of 4. I'm going to call this f of 5. And then I'm going to come over to here. And 4 is not in my list. So I'm going to call that f of 6. And I think you can see that as I continue this process, okay, I think you can see that what I'm doing is I am ultimately going to cover all of the positive rational numbers. Pretty clever, isn't it? So notice my list. Here's the first element, here's the second element, here's the third, the fourth, here's the fifth, the sixth, the seventh, the eighth, and you can see that what's going to keep going on is as I keep following this pattern and I keep diagonalizing like that, and it's going to cover all of them. So I have actually shown here that this function is 1 to 1, and it's also onto. Pretty incredible. So again, the order of this set right over here is equal again to this funny number. And again, we say it's denumerable. Okay, well, I think that it won't take you much convincing. If this is denumerable, then I would think that you would also realize that this is denumerable, all the negative ones. Okay? Now we're going to make a big, big jump. Suppose A1, A2, A3, and this goes on for infinity, are denumerable sets. So they are denumerable. Okay? Well, here's what I want to do. If A1 is denumerable, I can make a list of its elements. So I can come over here and I can say, well, A1 is really equal to little a11, and then it's equal to little a12, and it's equal to little a13. And this goes on forever and ever and ever. Remember, the fact that A1 is denumerable means I can give you a one-to-one function from the natural numbers to this set. Well, that's real easy. I'm going to let f of 1 be this, I'll let f of 2 be this, I'll let f of 3 be this, f of 4, etc., etc., etc. Now what I'm going to do is I'm going to come down here and I'm going to list the elements of A2. Now remember, A2 is also denumerable. So I'm going to make a list of the elements of A2. And I can do this for all of my sets here. A4, A41, A42. And remember, this goes all the way down. So these are the names of my sets, these are the elements in the set. Well, I think you can see what's going on here now. I can do exactly the same trick here that I did with the positive rational numbers. For example, I come over here and I look at this one here, and I go, well, that's f of 1. And then I come over here, and that's f of 2. And I come over here, and this is f of 3. And then I come down here, and then I go that way, and then I go that way. And again, you can see that what I'm going to do here is this ultimately is going to cover all of these elements here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You all get the idea. So we actually are getting a very, very theoretical result here, and I'm going to say the following. The innumerable union I should say the denumerable, I've been using that word, the denumerable union of denumerable sets is denumerable. Another way to say this is if A1, A2, A3 are all denumerable, then A equals the union from I goes from 1 to infinity of AI is denumerable. That's a very theoretical result. Remember, that's assuming this, that each one of the individual sets. Well, we're almost done. Remember before we said that that was denumerable, and because that one's denumerable, we know that this one is denumerable, and the only thing missing here now is 0. So I'll just add 0 here. So I'm going to take the union of this, and I'll take the union of this, and that's equal to all of Q. So the conclusion here is denumerable union a finite set, that's denumerable. So the conclusion here is that Q is denumerable. Well, you might be getting the feeling that everything's denumerable, so it's time to show you something that isn't denumerable. Okay, not everything is denumerable. I'm having a little trouble with my pen here. Not everything is denumerable. Okay, and I'm going to give you an example right now. What I'm leading up to is I would like to show you that the real numbers are not denumerable. But what I'm going to do instead is I will show, or we will show, okay, we will show that the following set here, set of all x, such that x is an element of R, and 0 is less than or equal to x is less than 1. I am going to demonstrate that this is not countable. Okay, remember, not denumerable. And what this is going to be is this is going to be a proof by contradiction. So I'm going to say, assume it is denumerable. Assume it is countable. Let's use a different word. Well, first of all, I want to review a couple of things. Remember that I can always write real numbers as a decimal. In other words, I can come, instead of writing 1/2, I can write 0.5. Okay? And we need to review or recall a couple of things here. If it's a rational number, we know that when we write it as a decimal number, it's either going to start repeating. Well, we know that it'll start repeating at some point. In this case here, it starts repeating like that. We know that if we have the number 1/3, it's equal to 0.333, and this keeps repeating. If the number is irrational, remember, we're not going to see the numbers ever repeat. It's just going to be, the numbers are going to keep changing. I don't want to say they're random, okay, but they're never ever going to, there's never going to be a pattern that repeats. So what I want to do is if we assume that it is countable, what I want to do is I want to make a list of these numbers, and I want to write them as decimal numbers. So I'm going to come over here and I'm going to say, okay, well, my first number looks like this. There's a decimal point there, and then there is, I'm going to call it D11, D12, D13, D14, and that goes on forever and ever and ever. For example, if this happened to be the number 1/2, and I don't know if it is or not, then this would be 0.5000, and it would keep going like that, okay? This would be D11, this would be D12, this would be D13, and so on and so on. So let's continue with our list. here's the second number, and the second number again is going to be D21, D22, D23, and this goes on forever and ever and ever. And here's the third number in my list, and it's going to be D31, D32, D33, and it goes on forever and ever. And this list here, of course, because we're assuming it's countable, we can just keep this list going. 1, 2, 3, 4, 5, 6, on and on and on and on and on. Okay? Now what I want to do here is I want to construct a number. And I'm going to construct a number here, D, just because that seems like a good letter to use. And what I'm going to do is I'm going to come over here and I'm going to take a look and see what that digit is. Now, if it happens to be the representation for 1/2, then it would be a 5. But I think you'll all believe that this could be any number. And what I want to do over here is I'm going to construct a number, and I'm going to call this D11, and I'm going to put a star over there. And what the star means is that this digit here can actually be any digit except that one. So for example, if D11 was a 5, this could be a 7, or it could be a 2. I don't care, all right? But then what I want to do is I want to come down here and I'm going to go down the diagonal again, and here is D22. And what I'm going to do over here is I'm going to say, all right, I want this number to be D22 star. And remember now what it means to be a star. To be a star means that D22 star is any digit except whatever this digit over here happened to be. And I'm going to do the same thing. I'm just going to keep going down this list. And again, you can see it goes on infinitely this way. And I'm going to construct a number over here, D33 star, D44 star. And you can see that this goes on forever and ever and ever. Okay? Now my claim is that this number D isn't in this list. And you say, oh, but Prof, it is in the list. And I go, where is it? And you go, it's at position J. Well, but I say that's impossible, because if I come way over here, there's a digit over here called digit DJJ. And over here is this digit J. And remember, J is point DJ1, DJ2, and we come all the way out here to DJJ, and it keeps going. And by construction, this digit here is different than this digit here. So if these two digits are different, then this number here can't be this number here. So the conclusion is I constructed a number that's not on the list. Now you say to me, okay, I understand, and oh, by the way, I made a mistake over here. I forgot to include this number. What I'm going to do now is I'm going to include it in the list. And I say to you, that's fine, but if you do that, then I can just as easily construct another number that's not on the list. So the conclusion here, this is false. Okay? And what I have shown you here is that the interval, okay, sometimes it's written this way, from 0 to 1, this is not countable. I can't make a list. Any list that you claim you have of it, I can always find a number that is not on that list. And I would claim that because this is a subset of this, that R is not countable. Okay, so here's an interesting thought question. We looked at this set before. Okay, and again, if you think of the real number line, and here is the number 0, and here's the number 1, and we're including the number 0. So it's, if I were to color this all in, everything except that spot right there. Okay, we said that that was not countable. And we said that that's a subset of all of the real numbers. Remember, all the real numbers would go all the way this way and all the way that way. And the question I have is the following. Let's give this set a name here. I'm going to call it A. And I'm going to say, is there a one-to-one onto function f that goes from A to R? And the answer to that is yes, and I'd like to show it to you. And again, this is going to be a different kind of way of showing things to you. I'm not going to explicitly give the function here. I'm going to kind of draw a picture of it for you. So the idea here, first of all, what I want to do is I want to take this line between 0 and 1, and what I'd like to do is I would actually like to roll it into a circle, if you will. So maybe the way that I can roll it into a circle is I start over here, here's 0, and I'm going to roll it all the way around, and it's going to come back over to there. This is right over here would be the open interval, the 1. So if we do it that way, you can think about it this way. This point right here is 1/2, and this point right over here, that's 1/4, and this point right over here is 3/4. Okay, I hope everybody's getting that. I'm sitting here waving my hands. I know you can't see that. But I'm just basically picking this line up and I'm rolling it into a circle. And here's my circle. And now what I want to do is I want to put that circle. Here are the real numbers. Okay. And over here I'm heading off towards positive infinity. And over here I'm heading off towards negative infinity. And here's how I want to create this function. Basically, what I'm going to do is I'm going to say that this point right here, 1/2, gets mapped right down here to 0. And what happens here is I am just going to draw lines from this point right here. I'm going to draw a straight line over to here. Now, this corresponds to some number here. It looks like it's a number that's slightly bigger than 3/4. And I'm going to say that my function, we can call it f, is going to go to this real number over here. And I think you can see that I can do this way over here. In other words, what I'm going to do is I am going to be drawing points. I'm going to pick any old point I want on the real number line. And what I'm going to do is I'm going to draw a straight line up to this point, 1/2. For example, let's try this one right here. And I'm going to say, look, f of 1/4, f of 1/4 is this number right here, which is some negative real number. And I think that you can see that basically what this is doing is that from any point here to any point on this long line here, when I draw a straight line, it's going to intersect this circle in exactly 1 point. That's my mapping. The mapping from the set A to the set R would be from this point on the circle to this point on the line right here. We can see that this is clearly 1-to-1, and it's also clearly onto. So what I've done here is I have actually provided a one-to-one onto function from one uncountable set to another uncountable set. Okay, I promised you we were going to talk about different kinds of infinities, and we're almost there. But first I want to just do a little review. Suppose I have a set A, and it's equal to 1, 2, 3. And you may recall we talked about this thing called the power set of A. And the power set is the set of all subsets of A. So for example, the null set is a subset of A, and we know that this is a subset of A. One, two, 1, 3, 2, 3, and then 1, 2, 3. This is the power set of A. And we know 1, 2, 3, 4, 5, 6, 7, 8. Remember, we said that if the order of A is equal to n, then we said the order of the power set of A is equal to 2 to the n. All right, well, now I want to return to this set here, the natural numbers. And what I want to do is I want to consider the power set of the natural numbers. All right? Now, here's the thing that I want to note about the power set of natural numbers. I claim this is not countable. And I need to prove that to you. And the proof is really not that hard. It's very similar to the proofs that we've done before. What I need to do is I need to consider what elements of this looks like. So for example, one element of the power set of P of n might look like this. It might look like 1, 2, 5. And another element of the power set might look like this. 2, 4, 6, 7. And again, we can imagine other ones. Remember, these are all subsets of this. Now, what I want to do is I want to write this in a different way. And what I'm going to do is I'm going to start counting, and I'm going to say 1, 2, 3, 4, 5, 6, 7, and this goes on and on and on. And I'm saying that this represents this set. Notice what I'm doing here is if a number is an element of the set, I'm just indicating it by a 1 in that position. 1 is in that set, so I set the first digit here to 1. 2 is in that set, so I set the second digit to 1. 3 is not in the set, so I set this third position to 0. 4 is not in the set, so I set the fourth digit to 0. 5 is. There's my 5. There are no other elements in the set. So this element right over here looks like the following. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, and then everything else is zeros like that. So, to prove that the power set of the natural numbers is not countable, we're going to resort to a same trick that we've used before. I'm going to say, assume it is. And I'm going to say the following. Assume the power set of n is countable. Okay, make a list. And I'm going to say the first element in the list looks like this. And I'm just making these numbers up. And actually I'm going to say it's really digit 1, 1, digit 1, 2, digit 1, 3, where each one of these digits is either a 0 or a 1. And here's the second element in the set, 0, 1, 0, 1, like that. And again, so that's digit 2, 1, digit 2, 2, digit 2, 3, and it goes on. So this list goes on infinitely. These numbers go on infinitely. And again, I get this list over here, D31, D32, D33. And remember, each one of these individual digits, it either corresponds to a 0 or a 1. If there's a 1 there, it means that that particular integer is in this subset. And if there's a 0 there, it means that that particular integer is not in it. Now, I think you can see where this argument is going. I'm going to create a new number here, and I'm going to say let it be D11 star, D22 star, D33 star, and it keeps going. In other words, what I do is I look at these, and now my rules here for swapping numbers is pretty easy. If this is a 1, I make that a 0. If this is a 0, I make that a 1. So what happens here is that I create this new number here, and I claim that this number is not in the list. The argument goes just like before. You say it is in the list, and I say, where is it? And you go, well, it's at position J. And I go, but wait a second. We have a number over here, DJJ star. And by definition, this number here was chosen such that DJJ star doesn't equal DJJ. Therefore, this number right here is not in the list, and we have a contradiction. So the conclusion is that P of n is not countable. Okay? But we have something even more powerful to show here. Okay, so we said that we could represent, again, if I had a subset of the natural numbers, and maybe it looked like this. And we said what we're going to do is we're going to rewrite that as 1, 2, 3, 4, 5, 6, 7, and then there are a whole bunch of zeros. Okay? Well, what I want to show you right now is I claim that there is a one-to-one onto function from the power set of the natural numbers to the interval that. Okay? And actually, this is going to be really cool. What I want you to do is I want you to come over here and look at this representation for this set right over here. And now what I want you to do is I want you to stick a decimal point in front of it. And now what I want you to do is I want you to think about this as a binary number, okay? But it's a binary number that has a decimal point in it. So let's remember something over here. When I write a number like this, 27.16, that's actually equal to 2 times 10 to the first plus 7 times 10 to the 0, and then it's plus 1 times 10 to the minus 1 plus 6 times 10 to the minus 2. Okay? Remember, 10 to the minus 1 is a tenth, 10 to the minus 2 is a hundredth. So it's really, this is tenths, this is hundredths. When I come over here and I look at this as a binary number, I'm doing the same thing here. Now remember, I've got a decimal point. Once I get past the decimal point, my exponents turn negative. And seeing that these are, this is in base 10, I see 10s over here. When I come up here, I'm going to want to do these in powers of 2. So that really means that this thing over here really represents a half. And this thing over here really represents 1 over 2 squared, which is equal to a fourth. And I think my 1 just went off your screen, but that's 1/4. This is 1/8, 1/16, 1/32, 1/64. So this number over here is 1/128. So this number over here is really equal to 1/2 plus 1/4 plus 1/128. And that's equal to, well, that would be 64 over 128 plus 32 over 128 plus 1 over 128. And that is equal to 64. That would be 96. That's equal to 97 over 128. Okay? So what I can actually do here now is any subset of the natural numbers can be converted into a binary number, okay? But it's a binary number with a decimal point in front of it. And then what I can do is I can convert those fractions and combine them, okay? And in this way, I think you're willing to believe, all right, that first of all, I guess what you need to think about is that I can express any number between 0 and 1 this way. And the answer is I certainly can do that, okay? So what I have here is I actually have a one-to-one function, okay, from the set of subsets of the natural numbers onto the unit interval right over here. Well, actually, if you think about it, we've done something pretty cool. We have a function here, f, that takes p of n to the unit interval. And if you remember the last slide, we had a function g that takes the unit interval all the way to r. So this is a one-to-one onto function. This is a one-to-one onto function. So that if I come over here and I talk about g of f of some x, where x is contained in the power set of n, this actually maps the power set of n all the way over to the real numbers. Pretty clever. There's just one more thing to talk about here. Okay, you may recall if we had a set A and the order of A was n, then the order of the power set was, or like this, was equal to 2 to the n. So what we have here is really kind of cool. Remember, we have the natural numbers, and we said the order of the natural numbers was this funny looking letter, Aleph Null. Just following the same reasoning here, that would say that the order of the power set of the natural numbers is equal to 2 to the Aleph Null. And realize that this is also equal to, just by the last slide we had here, that is equal to the order of the real numbers. Now, this is a different kind of infinity, okay? We have this thing called Aleph Null. Again, Mr. Cantor, 150, 200 years ago, he gave this a new name, and he called this Aleph 1. Now, by extension here now, here's something for you to think about. What about the power set of the real numbers? And again, that would be equal to 2 to the Aleph 1. And again, Mr. Cantor decided he was going to call that Aleph 2. And you can continue this on forever and ever and ever. So you end up, I'm almost done, and this is very interesting. We have this one kind of infinity here, which is less than this other kind of infinity here, and it's less than, and we just keep considering the size of the power sets to less than 3. And it goes like that. And again, Cantor came up with a very interesting question after he came up with this identity over here. First of all, recognize these numbers are really far apart from each other, okay? The difference between n and 2 to the n tends to get bigger and bigger as n gets bigger and bigger. So if n goes all the way up to Aleph Null, 2 to the Aleph Null is really far apart. Cantor wondered, are there any numbers in between these? And that's a very interesting question, and I'll leave it to you to look up the answer.